Hey, hello, and welcome to Woven Chemistry. I'm Jean Weaver, and this is the first of a three-part series of videos in which we're going to focus on standardizing a sodium hydroxide solution. Part 1 is unlike most of my videos, where I'm just going to explain what titration is and why we would need to standardize a sodium hydroxide solution. Part 2 gets back to my normal mode, in which I'm going to ask you questions that probe your understanding of the procedure for standardizing a solution. It's not about whether you remember the procedure, it's about if you understand what we do and why. And then part 3 takes your thinking up definitely another notch to that AP or college level, where I'm going to propose a number of errors and mistakes that may have happened during that procedure, and then ask you what impact they might have on your calculated results. Okay, so with that said, let's get started on what a titration is. So titration is a common technique used in chemistry to determine the concentration of a solution. Often it's used with an acid or a base, but it doesn't have to be. And there's an acid of unknown concentration that's neutralized with a base of known concentration, and the volumes that are combined are used to calculate the unknown molarity. And you can also do it vice versa, in which the base has the unknown concentration and you're using an acid of known concentration. Okay, so let's take a look at this in more detail. Here's our hydrochloric acid, and we don't know its concentration, and we're going to neutralize a part of that with sodium hydroxide of 0.75 molar. And just like it says up here in blue, we need to know the volumes of those solutions that we combine. And then here's the strategy. If we take advantage of the definition of molarity, we've got the molarity of the sodium hydroxide, we have the volume, we can easily calculate the moles. And since these react in a 1-to-1 ratio, we now can calculate the moles of HCl. Now we go back to this definition of molarity, and we've got the moles and we have the volume. We can easily calculate the concentration of that HCl solution. So it's all pretty simple. Now, if we want to have really good results, there's a couple of things we need to do. We need to measure carefully and accurately. Well, obviously, what device is best for measuring volume? Well, a burette. Burettes are really handy devices that work really well in titrations. So they're long, skinny cylinders that will fill up with our solution. And then down here is this stopcock. And this little blue rectangle here is kind of like a handle that you can turn 90 degrees, 180 degrees. Whenever it's fully vertical, then it exposes this little hole here and it allows the liquid to drain out. Okay, so what we'll do is we'll put a flask underneath, we'll open this little stopcock up, and we will let the HCl drain out. Okay, so when we're done, we close that up. We have some HCl down here, and remember, we need to know the volume that is here. So the trick to that is record the initial volume in the burette and the final volume, and the difference is going to be how much is in our flask. Okay, the burette is going to be much more accurate for measuring volume than the flask ever will be. Now, if you look at these volumes, you might be saying, well, wait a minute, why is the final volume greater than the initial volume? And if you look a little closer, when the burette is full, okay, the liquid is close to the 0 mark. Well, how can that be? The big numbers are supposed to be on the top. This is because burettes are designed for delivering liquid, not for holding it and knowing how much is in it. We want to know how much left the burette. Okay, because whatever leaves the burette is actually in our reaction. We don't care how much is in it. So the difference in the volumes will give us the volume that we used. Okay, so now the other thing we need to do is when you do a titration, you cannot have any excess reactants, right? Remember we said there was a 1-to-1 reaction ratio, no excess. Well, how are we going to know at the microscopic level when all the H+ has been reacted with the sodium hydroxide? The key is we're going to add phenolphthalein, acid-base indicator. That will turn pink as soon as all of that HCl has been reacted. So we can see macroscopically what's going on microscopically. So we'll slide that flask over, we'll turn that stopcock, we'll drain a little bit more sodium hydroxide into this flask, and we should really do it drop by drop because we want to know precisely the exact volume. So when it turns pink, we stop. We record the initial and final volumes, and we're all set to go with our calculations. So here we go. Here's our volume of HCl, 30 milliliters, and we use 20 milliliters of sodium hydroxide. So now let's actually go through these calculations. we're going to use the molarity equation, and we have molarity and we have volume, so we can calculate the moles, and we find that we have 0.015 moles of NaOH. The second thing we do is we use that reaction ratio to figure out that we had 0.015 moles of HCl in our flask. And now we have the moles and we have the volume. So 0.015 moles divided by the volume in liters gives us a 0.5 molar HCl solution. And that's all you have to do, pretty simple. Okay, now the accuracy of this calculated acid concentration depends on two things. The first we already talked about, the accuracy of the volume measurements, which we've covered with the burettes and the phenolphthalein. But it also depends on the accuracy of this number, the concentration of the NaOH, okay, because we're using that in the calculations. All right, well, let's think about that and what we can do to improve that accuracy. So here's an example. We're making 500 milliliters of a 0.1 molar solution of sodium hydroxide. Okay, we get out that molarity equation again. We solve for moles of NaOH that we're going to need. Then we use the molar mass, convert that to grams. Oh, we need 2 grams of sodium hydroxide. We go out, we get the balance out, scoop out carefully 2.000 grams of sodium hydroxide. Okay, then we get out a volumetric flask because that's going to be most precise in measuring 500 milliliters. We transfer those sodium hydroxide pellets into the flask. We add the water precisely up to the 500 ml mark. Okay, more precise than my little sketch here is. And voila, we should have exactly 0.1 molar sodium hydroxide solution. The problem is sodium hydroxide is hygroscopic. It absorbs water from the air, and it absorbs a lot. So let me show you an example. Here's those sodium hydroxide pellets, and these were exposed to the air for like 2 minutes, okay? 2 minutes between when I took this picture and when they were in the bottle. I took a similar number of sodium hydroxide pellets, put them on this watch glass, and then I put them outside in Wisconsin in the summer on a humid day and came back in 2 hours. And look at the difference here. They absorbed a lot of water vapor out of the air. And yes, that was 2 hours, but let me say that this one, when I was all done with the picture and I looked at these pellets, they were glassy. I could already see signs of water being absorbed to them. So then that means back over here, when the balance tells us we have exactly 2 grams on it, well, we have exactly 2 grams on it, but it's not only sodium hydroxide. There's water contaminating that, which means we have less than 2 grams of sodium hydroxide, which means that our concentration over here of our solution is less than 0.1. And we can't tell how much water we have here, so we're always doomed. We're never going to know precisely what that sodium hydroxide concentration is, which is why we need to standardize the solution, which means we need to titrate it to determine its exact concentration before we can use that solution to titrate something else. All right, so let's now talk about that standardization. When we standardize a base solution, you usually use a solid acid, and it's typically potassium hydrogen phthalate, which we'll abbreviate KHP. So that KHP is a monoprotic acid. It'll react in a 1-to-1 ratio with the sodium hydroxide, whose concentration we don't know. So like I said, we use solid KHP because we can measure it very precisely. We put that into a flask, and then we need to add some water so that it dissolves and it can react readily with the sodium hydroxide. Now, it's not important to know what the concentration of that KHP is, so we don't really need to know what the volume of water was. And that's because if we have the mass, we can calculate the moles. We can use molar mass. So molarity, Na, stands for not applicable. Doesn't matter at all. Okay, let's get on with this procedure. What we're going to do is we're going to set up a burette, fill it up with sodium hydroxide. In order to tell when all of that KHP has been neutralized, we put some phenolphthalein in there. We start dropping that sodium hydroxide into that drop by drop, and as soon as it turns pink, we stop. We need to know the volume, so we record the initial volume and the final volume. So we have the known volume. And now if we think this through a little bit further, we've got the calculated moles, the known volume of the NaOH, so we can take advantage of that 1-to-1 reaction ratio. So now we know the moles of NaOH and we know the volume. Geez, now we can use the definition of molarity again, moles per liter. and we can calculate the concentration of that NaOH. Okay, it's very, very similar to the previous example with HCl and sodium hydroxide. The calculations are a tiny bit different. So here, let's go through an example with the actual numbers. We've got 0.3072 grams of KHP. We need to know the moles, so we just use the molar mass of 204.22 and convert that to moles. And since we have a 1-to-1 reaction ratio, then we also know that we have 1.504 times 10 to the minus 3 moles of sodium hydroxide that we added. Well, now since molarity is moles per liter, we've got the moles, we convert the 15.7 milliliters to liters, and we can very easily calculate the concentration of that solution. Okay, so very, very simple. Now let's just kind of step back and kind of review everything we talked about here. So a titration is a technique used to determine the concentration of a solution, okay, and its accuracy depends on the volume measurements. And we mentioned that we can take care of by using the burettes and by using phenolphthalein. And then the accuracy also depends on how accurately we know this base concentration. And we figure that out by standardizing it, which is just a fancy name for a titration. And we have to standardize it because sodium hydroxide is hygroscopic. It absorbs water out of the air. So we don't know precisely how many grams of sodium hydroxide we have in a solution. So we're not going to know its concentration accurately unless we standardize it. So there you go. There's the what and the why of titration and standardization. Come on back for part 2, where I'm going to give you questions that probe at your understanding of the procedure. Okay, don't worry about remembering it. Don't worry about remembering what to do in the calculations. The questions will be about whether you understand what we do and why. Okay, so thanks for joining me, and I hope you come on back for the next video.